Good morning, dear students. This is the first lecture in the lecture series for Module 1 of ECT201 Solid State Devices. And this lecture series is being prepared by myself, Bonifus PL, Dr. Simi, and Ms. Jasmine. The first module will see some basic concepts in semiconductor physics. First of all, we will see what is meant by semiconductor materials. So, semiconductor materials are materials whose conductivity magnitude can be varied in large extent by changing temperature, optical excitation, and empirical current. Also, these semiconductor materials are found in column 4 and neighboring columns of the periodic table. You see. So, we'll see what is meant elemental and compound semiconductors. Elemental semiconductors are semiconductor elements found in the group 4 of the periodic table, column 4 of the periodic table. Example, silicon and germanium. Now, compound semiconductors are there. It can be binary compound, tertiary compound, or quaternary compound, etc. Now, if it is binary compound, it will be formed by combining elements in group 3 and group 4 of the periodic table, say like aluminum, aluminum arsenide, aluminum phosphide, gallium phosphide, gallium arsenide, etc. Similarly, we can form binary compounds by combining elements of the group 2nd and 6, like zinc sulfide, cadmium sulfide, etc. We can also form binary compounds within the elements in 4th group, such as silicon carbide, silicon germanium, etc. Now, it is possible to create ternary compounds such as gallium arsenide phosphide, aluminum gallium arsenide, and it is also possible to form quaternary compounds like indium gallium arsenide phosphide. And these semiconductor materials are being used in a wide variety of applications, like in PN junction diodes, in LEDs, in lasers, etc. So you may find out the uses and properties of these elements and its applications. Now we will see some fundamental concepts. First of all, we will start with the fundamental concepts of metal, semiconductors, and insulator. Then we will see what's the concept of electrons and holes. Then we will see what is meant by intrinsic semiconductor and extrinsic semiconductor. Then we will see the concept of effective mass. Now we will distinguish metals, semiconductors, and insulators with respect to their band diagrams at 0 Kelvin. For metals, we will be having a fully filled valence band and a fully empty conduction band separated by a very large energy gap, Eg. Normally, this Eg will be more than 10 electron. If it is for semiconductor, structure will be similar. We'll be having fully filled valence band and fully empty conduction band. But the difference between this conduction band and valence band is small. This Eg will be something near to 1 electron volt or below 1 electron volt. So the difference is that when you have some sufficient energy for insulator, you need some very high energy to move electron from valence band to conduction band, which is generally not possible. But in case of semiconductor, with the application of very small energy, you can move electron from valence band to conduction band, and it is possible to create conduction. Next is metals. In metals, there are two possibilities. Either the conduction band and valence band can overlap, or there can be a fully filled valence band and a partially filled conduction band separated by a small distance. In both cases of metal, conduction is possible. Because in the first case, conduction band and valence band are overlap, so there is possibility of electron movement from valence band to conduction band. And in the second case, a valence band is not empty, it is partially filled, so there are some electrons to move. Also, if your conduction band or valence band is fully filled, conduction is not possible. You need some empty space also, then only conduction is possible. Now we will see the fundamental concept of electrons and holes. So what all things we will say for electrons? For holes it will be just opposite. For example, for electron the charge is negative, for hole the charge is positive. The electron is moving from right to left, correspondingly hole will be moving from left to right. Like this. So here we see the previous diagram. For semiconductor we have seen a fully filled valence band and an empty conduction band, right? Spherical. Suppose we are giving some sufficient energy, then some electrons in the valence band will move from valence band to conduction band. So that is shown over here. The black dots are electrons. So when we apply some energy or some sort of excitation, electrons from valence band will move to conduction band. So in the conduction band we have now electrons which is from valence band, which is named as black dot. And once electrons move from valence band to conduction band, we are having empty spaces, which is denoted as white dots, which are otherwise called holes. So in a semiconductor, these electrons and holes are always created as space. That means once you move electron from valence band to conduction band, there will be an electron in the conduction band. Correspondingly, you are having vacant space or hole in valence band. Now we will see the concepts of intrinsic semiconductor and extrinsic semiconductor. Intrinsic semiconductor means it's a pure semiconductor, and extrinsic semiconductor means it's a doped semiconductor, or you have added some impurity to that in semiconductor. It is called extrinsic semiconductor. So first of all, we see what is an intrinsic semiconductor. So as we said, intrinsic semiconductor is a pure semiconductor. There is no dopant added, or there is no impurity added. For silicon, now we will be discussing about with 4 elements, either it can be silicon or germanium. So most of the times we will be talking about silicon. For silicon or gallium, silicon or germanium, at the outermost shell we will be having 4 electrons. So these 4 electrons will form 4 covalent bonds with 4 of its neighboring atoms. So that is shown over here. Each atom has formed 4 covalent bonds with 4 of its neighbors. That will be these atoms in silicon. So once you give some sufficient energy, some of this covalent bond may break, and you will provide one electron, and you are having one incomplete covalent bond. So that incomplete covalent bond will act as a hole. This electron and hole can move along the lattice structure, which can contribute to conduction. But provided you need to provide sufficient energy, and number of electrons and holes created by this normal covalent bond break will be minimum. And for intrinsic material, we will call number of electrons will be equal to number of holes, which is N is equal to P. That means once you break a covalent bond, you are having 1 electron and 1 hole. If you break 2 covalent bonds, you will be having 2 electrons and 2 holes. So this number of electrons will be equal to number of holes, and as it is intrinsic material, we will denote both these quantities using the term N suffix I. For extrinsic material, we'll be adding some impurities to the intrinsic semiconductor. So the impurity can be either trivalent impurity or pentavalent impurity. If you are adding pentavalent impurity, that will call those impurities as donor atoms. That means this pentavalent impurities will donate one electron. This trivalent impurity, we will call it as acceptor atoms because it is having only 3 electrons at the outermost shell. So suppose initially we are adding donor atoms. So the left hand side the band is the band diagonal T equal to 0 Kelvin, and the right hand side is the band diagonal at temperature T equal to 50 Kelvin. Now when we add donor atoms, a new energy level which is called ED will be created near to the conduction band of the semiconductor. This ED will contain electrons, or this ED will be fully filled. Now what's the advantage? Earlier, if you need to make the semiconductor as conducting, you need to move electron from valence band to conduction band. Now we are having another energy level ED near to the conduction band, which is fully filled. So we need to just move electrons from this ED to conduction band. So you need only that much energy. So that is shown at the right hand side. When you give some extra temperature, that is T equal to 50 Kelvin, electrons at the ED level get enough energy to move to conduction band, and which will contribute to conduction. And for extrinsic material, we will be having two other terms: equilibrium electron and hole concentration. Equilibrium electron concentration will be indicated as N0, and equilibrium hole concentration will be indicated as P0. And Ni is equal to Pi, which is nothing but intrinsic electron and hole concentration that we have seen in the previous slide. And for extrinsic material, this equilibrium electron hole concentration will be very much higher than equilibrium hole concentration as well as intrinsic electron concentration. Now we will see the case of p-type semiconductor. For p-type semiconductor, we will be adding trivalent impurity or acceptor impurity. So when you add acceptor impurity, a new energy level will be created near to the valence band, and this new energy level EA, which will be empty. So here, with a small application of energy, you can move electron from valence band to acceptor level, thereby creating holes or vacant space inside the valence band. And this vacant space or holes inside the valence band can contribute to conduction. Here, the equilibrium hole concentration P0 will be very much greater than the equilibrium electron concentration N0 and intrinsic electron or hole concentration Ni. So these are the band structures of extrinsic material. We will also see the bond formation. If it's pentavalent impurity, it may be, for example, it can be arsenic. If it is arsenic, it is having 5 electrons at the valence shell. So it will form 4 covalent bonds with 4 of its silicon neighbors. But 1 electron is left out, and this electron can contribute to conduction. If it is trivalent impurity like boron, it is having only 3 electrons at the outermost shell. So it can form 3 complete bonds with 3 of its silicon neighbors, and 1 bond will be incomplete bond that will act as hole. Next concept we are going to see is effective mass, and for effective mass we'll denote the symbol M asterisk, and if it is for electron we'll denote using Mn asterisk. For holes we'll denote it using B asterisk. Now we know electron is there in all the materials. Whether the mass of electron in all of these materials are same or not, that concept we are going to do. So if it's same material, whether it can be silicon, germanium, gallium arsenide or any other material, the true mass of an electron M will be same, and for true mass we'll be using just M. If it's effective mass we'll use the term M asterisk. Whatever material you take, the true mass will be same, which is same as that of the mass of an electron kept in vacuum. That means for that electron there is no external forces applied. It is purely free. But effective mass is different from true mass. So we said true mass is a mass experienced by an electron which is kept in vacuum. It doesn't experience any sort of force. But once there is an external force experienced on an electron, this electron will respond to the new force or this external force with a new mass which is called effective mass, and it is denoted as Mn asterisk. So for different materials we will be having different lattice structures, and based on these different lattice structures periodic crystal forces will vary, and these periodic crystal forces depend on the details of a semiconductor, a specific semiconductor. Therefore the effective mass is different in different materials. Now we are going to deal with the concept of carrier concentrations, that is nothing but the concentration of electrons and holes. So to study that we need some concepts. So Fermi level, then we see electron and hole concentrations at equilibrium, then we see what we mean by equilibrium and steady state conditions, and in the next part we will see the temperature dependence of carrier concentration. Now we will see what is Fermi level. Electrons in solids obey Fermi-Dirac statistics. This Fermi-Dirac statistics is being developed by considering the indistinguishability of electrons, their wave nature, and Pauli's exclusion principle. And this Fermi-Dirac statistics is given by the expression f of E equal to 1 divided by 1 plus e to the power e to the power e minus ef divided by k into t. Here k is Boltzmann constant. Its value is 8.62 into 10 raised to minus 5 electron volt per Kelvin, or 1.38 into 10 raised to minus 23 joules per Kelvin. Here we will be using the values in electron volt per Kelvin. F of E is the probability that an available energy state at E will be occupied by an electron at absolute temperature T, where EF is the Fermi level. Now we will see the occupancy probability at different energy levels. That means for E we will be substituting some values. If E equal to EF, if E equal to EF, then in this expression it will be E to the power EF minus EF. That means 1 by 1 plus e to the power 0. That means 1 by 2. So if E equal to EF, the occupation probability is 1 by 2. Now, assume the temperature is always at 0 Kelvin. That means in this expression f of e equal to 1 by 1 plus e to the power e raised to e minus ef divided by kt, in which this temperature is always 0. That means it will be e to the power infinity. It can be plus infinity or minus infinity based on the value of e and relative values of e and ef. If e is greater than ef, it will be plus infinity, e to the power plus infinity. If e is less than ef, it will be e to the power minus infinity. Now, when e is less than ef, will be having 1 divided by 1 plus 0. So the occupation probability is 1. When e is greater than ef, f of e equal to 1 by 1 plus infinity, which is equal to 0. So the meaning is this: if we plot f of e against E, there is an energy level EF. Up to EF, the occupation probability is high 1. That means you are having very high probability of getting states occupied by electrons. And beyond EF, if E is greater than EF, the occupation probability is 0. That is no probability that electrons will be filled. And at the point E equal to EF, our occupation probability is 1 by 2. So the meaning is that every available energy state up to EF will be filled with electrons, and all the states above EF are empty. And now we have assumed that temperature to be 0 Kelvin. Also we said f of E is a probability distribution. So the area under this probability curve will always remain same. Now what will happen if temperature is greater than 0 Kelvin? Now if temperature is greater than 0 Kelvin, there is probability that electrons can be filled beyond states EF. That means there is some probability of occupancy above states EF. But we need to keep the area under the f of e curve as same. Then it is necessary that some of the states below EF should not be filled. So that's shown over here. We are having two temperatures, T1 and T2, which is greater than 0 Kelvin, in which T2 is greater than T2. Suppose we are increasing energy temperature to temperature T1. Now there is some probability that some states above EF can be filled. Then there is some probability that some states below EF won't be filled. Similarly for T2 also. So at T equal to T1, there is some probability f of E that states above EF will be filled. Now there is a corresponding probability 1 minus f of E that states below EF are empty. So for the electrons we will be calculating the probability f of E, and for holes we will be calculating the probability 1 minus f of E. So the probability f of EF plus delta E, that is state delta E above EF is filled, is the probability that same as the probability 1 minus f of EF minus delta E, that is state delta E below EF is empty. Means some state above EF will be filled. The probability of that will be equal to some state below EF which won't be filled. So those two probabilities will be equal. And f of E is symmetrical about EF for all temperatures. Therefore, a natural reference point in calculation of electrons and proton concentrations. Now we will be relating this Fermi level to intrinsic semiconductor and extrinsic semiconductors. For that purpose, we will be rotating this f of e against e plot 90° anti-clockwise. Likewise here, it's the same plot as we see in the last slide. F of e against e is 90° rotated anti-clockwise, and to the energy axis we have plotted conduction band, valence band, Fermi-Dirac. And for conduction band, lowest energy will be using the notation EC. For the valence band, topmost energy will be using the notation EF. This for EV. First of all, we will be seeing the intrinsic material. For intrinsic material, at 0 Kelvin, we won't be having any electrons at conduction band. When you apply some sort of energy, some electrons to conduction band. And for intrinsic material, the Fermi level will always lie at the middle of the energy gap. Also, the concentration of holes in valence band will be equal to the concentration of electrons in conduction band. Because here we don't have any excess electrons or excess holes. Whatever electrons are excited from valence band will reach conduction band, and the equal amount of holes will be there in valence band. Now, in this curve, we are having electron probability tail and hole probability tail. Electron probability tail means when we plot this curve, there is a gap. This gap difference near to EC, which is the probability of finding electrons in the conduction band. Similarly, we can have a value 1 minus f of EV near valence band EV, near to EV. So these two values, that is f of EC and f1 minus f of EV, that is electron probability tail and hole probability tail, these two should be symmetrical. And if we consider the values of f of E, so within this energy gap, f of E is changing and f of E is having some values, but there are no energy states available within each. That means there is no occupancy of electrons or holes inside energy gap each. Next, we are seeing Fermi level for n-type material. For n-type material, we will be having a higher concentration of electrons in the conduction band compared to holes within valence band. Because of that, EF should lie near to the conduction band. So definitely, the electron probability f of EC will be having a high value compared to the hole probability 1 minus f of EV. And f of E for each energy level in conduction band increases as EF moves near to conduction band. That means once EF moves near to conduction band, this curve will also shift upwards. That means this gap will increase. That means we are having a more value for electron probability. And for n-type material, the difference between EC and EF will give a measure of electron concentration. That means if EF is near to EC or EC minus EF value is small, we are having a large concentration of electron in the conduction band. Next is the Fermi level for p-type material. If it is for p-type material, we will be having more hole concentration in valence band compared to electron concentration in conduction band. So definitely the Fermi level should lie near to the valence band. If Fermi level is lying near to the valence band, the f of E curve should shift downwards. That means the whole probability curve, that is 1 minus f of E, will be having higher value compared to electron probability f of EC. Now we are going to deal with the concepts of equilibrium and steady state conditions. Equilibrium condition means it's the condition in which there is no external excitation other than temperature and there is no net motion of charge. There means there is no motion of electrons and holes. You are not applying any sort of excitation other than the temperature. This temperature also should be constant. Now, steady state means it's a non-equilibrium state in which all processes are constant and are balanced by opposing processes. That means all non-equilibrium states are not steady state. A non-equilibrium state can be steady state if and only if all processes are constant and all processes are balanced by opposing processes. That means if you are having an electron movement, it should be balanced by an opposing hole movement. Again explaining, equilibrium means it's nothing but a thermal equilibrium state. That means we are having a constant temperature. And we have seen this Fermi levels, which was at the middle of the band gap at intrinsic material, near to conduction band at n-type material, and near to valence band at p-type material. So this Fermi level position will be constant, which won't vary at equilibrium condition. Now, steady state means, as the name suggests, the properties of the system do not change with time. Again, no equilibrium state can be steady state if there is a source of energy to maintain no equilibrium state. Let's see example. For example, you are having a PN junction diode. Simply you are having a PN junction diode. You haven't connected any forward or reverse bias or any source of voltage. Then that PN junction diode is in equilibrium because you don't have any external source of excitation other than the room temperature. Now you are connecting this PN junction diode either in forward or reverse bias. Now it will be in non-equilibrium state, but it will be in steady state, meaning that means that for an electron current there will be an opposing hole current. So we'll see all these things detailed in later. Now we are moving to the important derivation. The first module is electron and hole concentration at equilibrium. So the concentration of electrons in conduction band. To picturize the conduction band, valence band, and little further level, so the concentration of electrons in the top conduction band, which is N0, is equal to integral bottom of the conduction band, that is EC, to the highest energy, which is infinity. So integral EC to infinity, f of E into n of E to d. Explain. F of E, you know, is the Fermi-Dirac statistics or probability of finding electron in a particular energy level E. Now, n of E into d is density of states in centimeter raised to minus 3 in the energy range defined by d. We are having a large energy range from EC to infinity, in which we are considering a small energy d. So in that small energy range d, what is the density of states available? That means how many electrons or how many holes can be occupied. So which is termed as n of E to d. Then N0 and P0, we will be using some notations. So it's N0 and P0, that means electron and hole concentrations at equilibrium conditions. Number of electrons per unit volume in energy range dE is given by density of states into probability of occupancy. That is the expression. Now this n of E is proportional to square root of E. That means as energy increases, n of E should also increase. But f of E is extremely small for large energies. Earlier we have seen up to EF you are having some probability. Beyond EF the probability is 0. Even if temperature is greater than 0 Kelvin also, that probability will be very negligible. So this f of E value is extremely small. So extremely small quantity into a large quantity. So the product of f of E to n of E decreases rapidly above EC. Therefore, very few electrons occupy energy states far above conduction bandwidth. So that means most of these electrons will be occupied near to EC, which is the lowest most energy in the conduction band. Similarly, probability of finding a hole in valence band 1 minus f of E decreases rapidly below EV. That means the probability of finding holes is very high at the topmost energy level of the valence band, which is EV. Now we plot these concepts. So the first plot is the energy band diagram for intrinsic semiconductor. Then the plot of n of E against E. Then the plot of f of E against E. Then the multiplication of n of E into f of E against E. So for intrinsic semiconductor, the Fermi level lies at the middle of the band gap EF. Then for electrons, n of E is proportional to square root of E. That means n of E will increase as energy increases. Okay. So it will be just symmetric for holes. So the distribution is like here. Now the f of E curve. As we are having intrinsic semiconductor, EF is at the middle. The f of E and 1 minus f of E gap will be same. Now in the previous slide we said the concentration of electrons is given by f of E into N. So that is this value into this value. So that distribution is shown over here. Also, hole concentration, this value into this value, as shown over here. For intrinsic semiconductor, the concentration of electrons and holes are same. Now for n-type semiconductor, the Fermi level lies near to conduction band. That means this f of E curve will be shifted upwards. That means here you are having a larger gap. F of E gap will be larger and 1 minus f of E gap will be narrower. So this value into this large value, you are having large concentration of electrons. This n of E value into smaller 1 minus f of E value, we are having a smaller hole concentration. Next is for p-type semiconductor, EF is near to valence band. So the curve, f of E curve will be shift downwards. So 1 minus f of E will be having higher value compared to f of E. So you are having n of E into 1 minus f of E as higher value, which means holes are having higher concentration. Now, continuing with the derivation. So we have started with the equation n0 equal to integral AC to infinity f of E n of E dE. Now we will be refining this equation. This is particular equation 3.2. Assume that all of the distributed electron states in the conduction band are represented by an effective density of states Nc, which is located at the conduction band at EC, that is at the lowest most conduction band. Then the equation 312 can be modified as N0 is equal to Nc into f of Ec. We have removed that integral and we have assumed that all states are near to the lowest most conduction band Ec. Just modify the previous equation. Now, assume that EF lies several times kT below conduction band. Now we have the Fermi-Dirac statistics f of A equal to 1 by 1 plus e to the power e minus Ef divided by kT, in which we will be finding Fermi-Dirac statistics for lowest most energy of the conduction band, that is f of Ec. So here it is Ec, here also it will be Ec. Now assume that the gap between Ec and Ef is very large. So this quantity will be very high. So this equation can be approximated as e to the power minus Ec minus Ef divided by kT. Now the value of kT, we have seen the value of Boltzmann constant earlier, and the room temperature will be taking temperature as 300 Kelvin. So when you multiply these two values, you will get 0.026 electron volt. And at room temperature, this will be a good approximation. And in the equation 13, Nc into f of Ec. So f of Ec is e to the power minus Ec minus Ef divided by k. You substitute it, you will get the expression N0 equal to Nc into e to the power minus Ec minus Ef divided by kT. And this effective density of states Nc is given by 2 into 2 by mn asterisk kT by h square all raised to 3 by 2, where mn asterisk is effective mass of electron and h is Planck's constant. By similar arguments, we can find the concentration of holes in valence band. For finding holes in valence band, P0 will be equal to Nv into 1 minus f of Ev, where Nv is the effective density of states in valence band. And by similar arguments, we can write 1 minus f of E will be equal to e to the power minus Ef minus Ev divided by kT for larger Ef than Ev. Then concentration of holes in valence band. Similarly, you can find P0 equal to Nv into e to the power minus Ef minus Ev divided by kT. So compare the equations for N0 and P0. For N0, it was N0 equal to Nc into e to the power e minus Ec minus Ef divided by kT. For P0, it is Nv into e to the power minus Ef minus Ev divided by kT. Similarly, the effective density of states in the valence band is given by Nv equal to 2 into 2 pi Np asterisk kT by h square whole raised to 3 by 2. Compare its expression with Nc. For Nc, it was Mn asterisk. For Nv, it is Mp asterisk. Now, electron and hole concentrations are valid for both intrinsic and doped semiconductors at thermal equilibrium. That is the equations 15 and 19. Equation 15 is in N0 equation, that is N0 equal to Nc into e to the power minus Ec minus Ef divided by kT, and 19 is P0 equal to Nv into e to the power minus Ef divided by kT. And for intrinsic material, we said Ef lies at the middle of the band gap. So the middle of the band gap we will denote using Ei. So Ef will be equal to Ei. So in these previous equations 15 and 19, you can replace Ef with Ei. And for intrinsic semiconductor, we said we won't be talking about equilibrium concentration. Or equilibrium concentrations are equal to intrinsic concentration, Ni. So instead of N0 and P0 we'll be having Na and Pi, and for EF, instead of EF we'll be having Ei. So the expressions will be Na equal to Nc into e to the power minus Ec minus Ei divided by Kt, and Pi will be equal to Nv into e to the power minus Ei minus Ev divided by Kt. Now we will be multiplying equation 15 and 19. That is, we will be finding product of N0 and P0. Similarly, from equation 21, we will be finding the product of Na into Pi. So when you do that mathematical calculation, we will get both N0 into P0 and Na into Pi are Nc into Nv into e raised to minus Eg divided by Kt. So that means both are equal. N0 into P0 is equal to Na into Pi. That you will get. Now, for intrinsic semiconductor, is said intrinsic hole concentration is equal to intrinsic electron concentration, because how many electrons we are moving from valence band to conduction band, only that much electrons holes are there in valence band. So Na is equal to Pi. So if you substitute Na equal to Pi in this equation 322b, you will get it is Na square. So you can write Na equal to square root of Nc Nv into e to the power minus Eg divided by 2 Kt. So comparing these two equations, 322a, 322b and 323, you can write N0 P0 is equal to Ni square. So this equation is important equation that we will be using most all the problems. Now compare the equations 21 and 23. That is expressions for Ni in terms of Ec, Na and Pi in terms of Nc and Nv, and equation 23 is square root of Nc and Nv e to the power minus Eg divided by 2 Kt. So you compare those two. From those two set of equations, you can write Ec minus Ei equal to Eg divided by 2 if Nc is equal to Nv. That is, in this expression, substitute Nc is equal to Nv. Then you can write Ec minus Ei equal to Eg divided by 2. Also, another form of writing equations 15 and 19. 15 and 19 means N0 and P0 in terms of Nc and Nv, to which you can apply equation 21. That is this Na and Pi expression. Substitute for, rearrange these equations and substitute for Nc and Nv in 15 and 19. Then we will get the expressions N0 equal to Na into e to the power Ef minus Ei divided by Kt, and P0 equal to Na into e to the power Ei minus Ef divided by Kt. So the meaning is electron concentration is Na when Ef is at intrinsic level Ei. The first expression 325a, we have the expression N0 equal to Na into e to the power Ef minus Ei divided by Kt. So if Ef is equal to Ei, that is for intrinsic semiconductor, this term will be e to the power 0. That means N0 equal to Na when Ef is at intrinsic level Ei. Similarly, for holes, P0 will be equal to Na. Also, if Ef is not equal to Ei, N0 will increases exponentially, because we are having an exponential time as Fermi level moves away from Ei towards conduction band. Similarly, P0 varies from Na to larger values as Ef moves away from Ei towards valence band. So this is the first part of the lecture series for module 1. So here we have studied about the concept of the basics of semiconductor materials, Then we dealt elemental and compound semiconductors. Then we have seen the fundamental concepts of metals, semiconductors and switches based on the band diagrams. Then we have seen the concepts of electrons and holes, electron-hole pairs. Then we have seen concepts of intrinsic semiconductors and extrinsic semiconductors. Then we have seen the concept of effective mass and true mass. Then in the last section we have seen carrier concentration, in which we dealt with Fermi level. Then electron and hole concentration at equilibrium. Then equilibrium and steady state conditions. Then in the concepts of carrier concentrations, temperature dependence of carrier concentrations is also there. So that will be covered in the next session. Thank you.